Hey everybody, I'm just going to do I'm about to start because I've got a lot to cover and not very much time to cover it in. I'm going to just start off by giving a quick heads up that this is going to be very technically minded. There's going to be a lot of code flashing across the screen, especially shader code. I will be doing a bunch of sort of bits and pieces of live coding during it as well. So just sort of, if your only basics is roughly have heard of shaders, you might find this is going to be a little bit come at you pretty fast and thick. So hopefully no one will be left too far behind. But I will be doing some live coding during it, hopefully, so you will be able to see some step-by-step stuff. So even if you're not 100% aware of everything that I'm doing, then hopefully it won't leave you too far behind, and you'll be able to at least see some neat stuff associated with it. So I've got this is going to be, I'm sure you're all perky-eyed and have absolutely not got tired at this point. So we're basically jumping into a nice, very technically minded, difficult talk. So hopefully I will be leaving you all super duper exhausted. All right, so hi, my name's Blanche. I'm doing as many people know, I'm sorry everybody, I'm going to be ducking straight into it because again, I've got a lot to cover and I'm not going to get through it all. Most likely some of the lighting concepts are going to be left off at the end because I'm just not going to quite have time to get to them. But if you have any questions, you can come to me afterwards. I will be showing little bits and pieces of code from there. Anyway, so I'm going to be talking about some high-level shader concepts. The basic bringing it all together concept is really leading stuff to be much more generic and project-wise rather than having things quite so focused on a per shader basis. That is, and currently, and I'm sure a lot of people here do the same thing because I know I do it, you often end up coding a shader for every single possible function and you constantly have to set all the values on it. There's a lot of really useful stuff that you can do that will help you be able to streamline a lot of that. So we're going to be looking at global variables. We're going to be looking at matrices, CG include files, how to create your own ones. We'll be touching very briefly on some basic depth map information as well as a quick breakdown on how some of Unity's lighting actually works at an internal level. And we're going to be really heavy on the code, so there's going to be relatively few images to help people out here. My name's Blanche. I'm the director of one of the directors of Considerable Content, making a game called Rogue Singularity, which many of you will hopefully have seen or have a chance to see at this coming PAX. You can also find me on Twitter at TechArtEd, and I'm also the technical artist for Tin Man Games, working on a bunch of their projects. All right, so first of all, I'm just going to go through some really basic shader stuff, but I'm going to be moving very quickly, so don't panic. We're going to be ramping up. It's just going to help get some basic terminology and especially help because I'm going to be looking very focused on surface shaders at this point. That is because it's all very heavily integrated within Unity, but that being said, I will be touching very briefly on non-surface shaders, and a lot of the principles apply to both, especially because surface shaders are not as different from a vert and frag shader as people typically think. It's not a different language, it's not a different syntax, it's just you're editing the code in a different place, but it is essentially the same code. So the first definitional thing I'm going to be talking about is your property blocks, and specifically what we're essentially doing is we're taking a lot of the code that you need to write again and again, especially properties, and we're trying to abstract them into ways that are much more manageable on a project-wide scale. So that's where we'll be doing things of, instead of putting a property on a shader, you'll be declaring it globally from a script so that any shader in your entire workflow can then pull and read from what you need to in those circumstances. So in here you can just see, can you see my mouse up on screen there? Yeah, you can see here, this is a Unity input area that relates to the UI components of your shader, that is the properties that you can see visually. And then in here you can see the actual, whoopsie daisies, we'll go back. You can actually see here that you actually have to declare the variable itself before you use it. That's just that's the UI component of the property. So when you're doing a global property, you won't be writing it up here. It will just be featuring as a line item that needs to be declared within there. All right, so Unity's don't depend. Probably the first and the biggest piece of advice is don't depend on Unity's documentation. It's quite often out of date or very, very lackluster or lacks what you need to be able to know about it. I would not recommend going there. If you need or want to know how to do something, download Unity's built-in shaders. That is your starting point for everything, right? So as soon as you need a shader, go and find a shader that does something similar to what you need it to do, and then start pulling information out of there. Until recently, Unity's documentation did not account for the fact that they changed their blending modes. So I don't know, some people in here might have found that they're no longer, their multiplicative and transparent shaders no longer use their old blending modes, and so you need to be able to update them. So that can be a really important thing to do. So in order to get built-in shaders, you just go to the Unity website and pull down the sort of extra packages associated with it. If you just type in built-in shaders, you can get it for your current version of Unity. I have a version of it on this project here, and I'll be pulling it in a little bit just to show you some quick and easy internals. All right, so I'm going to jump straight in and actually start doing some of these coding bits and pieces live to help everybody sort of see what I'm doing step by step. You're all sort of my guinea pigs today because I've not tried this format before, but I did do sort of a semi-version of this format at another talk, and people responded to it fairly well, so hopefully everything that's up on screen is going to be reasonably readable. And now, just a heads up, I'm not actually going to be coding it live because the rest of this talk would just be me Googling and trying to remember everything that I'm supposed to know. So a lot of these shaders I just pre-wrote last night just to make sure that they're all going to work and function and I didn't make any too major mistakes before I all showed everybody. But we'll still be going through it step by step. All right, so first thing I'm going to do is just have a basic rundown on the concept of a surface shader. So a lot of people often trip or become confused at this. Probably one of the biggest mistakes that I constantly see people doing is the first thing they do is throw the surface shader straight out of the window and end up coding their own vert and frag shaders from scratch in order to try and integrate with Unity's lighting. In 90% of circumstances, you don't need to do this. And in fact, you're making your life much harder by doing it. Unity's surface shaders are actually relatively well integrated with their engine and have some efficiencies in there that you don't necessarily realize. And it does not always behoove you to immediately think that you can do it better, because in some cases you won't be able to, or in other cases you won't be able to replicate the behavior as easily exactly. So that's why I'm going to be focusing very much on using Unity surface shaders, because the more and more I do it, the more and more advantages I seem to be able to get out of them, but you just have to be prepared to be quite messy with how you do it. All right, so straight away, I'm going to jump up into, I think I got a blank project there. Can everyone see that? Yep. And can everybody see this? Can everybody read that fairly clearly? Awesome. All right, so here we are. This is actually just literally a blank shader that's been created for the purposes of being able to dump code in. So essentially, the difference between a vert and a frag shader and the surface shaders is that a surface shader is a vert and frag shader, but you don't edit the vert and frag components. What you edit is something called the surface out. Well, I mean, do most people here know what a struct is? Or at least have some vague idea of what a struct does. For those who don't, a struct is basically just a data structure that contains within it a set of known other simple variable values that can have one pointer so that it can find everything within it. So essentially, what a surface shader is just a function that assembles a struct. That struct is all the information that they need to be able to do their lighting calculations. And Unity's lighting calculations are its fragment pass. So its fragment pass is expecting an input variable, which is just a struct that is full of all of these individual values. A warning, if you're playing around with some of this stuff, as I've discovered to my own non-benefit. If you're programming for consoles, if you are on a PC or Mac, and Linux as well, I think, if you leave one of these struct values blank, it won't be a problem, but often if you're compiling for a console, what happens is you'll get a nan, and then if you get a nan, you get a really big problem, and everything will look horrible and distorted, because not a number multiplied by any number is not a number, and so forever everything is ruined. So that's essentially all it is. This surface output standard is just a struct. And all of these is we're defining each value in that struct. That is, the struct has an albedo, a metallic, a smoothness, and an alpha, or a normal and a what have you. So it's actually a very, very simple little process. So to start off with, inside this project, I'm going to drag in a pine tree. Boink. And the first thing that we're going to do is also throw in a plane for it to sit on top of. All right. So that's just using a Unity standard cutout shader. You can see that it looks fine and dandy. So what we want to do here, for instance, is I'm going to start off by making this tree wave in the wind. And then we're going to work out how to sort of upgrade some of that behavior and extrapolate from it. So here's the tree wind. You can immediately see straight out of the bat that obviously we don't have any of the cutouts, we don't have any of the other sort of performant things that we want. So first of all, we're going to quickly go in and we're going to set it up to function like that sort of cutout shader that Unity does. So the first thing that we want to do is, again, you can pull a lot of this from Unity's existing documentation. They have a lot of really useful blend modes that are actually built into the pragma directives. So in this case, if you want a pragma directive for cutting it out, you just go alpha test :_ cutoff, which I'm about to define. So there we go. Now in this case, it's a property. So what we want to do is we want to make sure that it's in the property block. Now again, you could do this using a global one, but usually you'd want to do this in in the actual property block of the shader, because there's very few circumstances where you would want it to be a global value. So straight off the bat, you can see that it's now cut out from it. But the first thing that you might be able to notice, and I'm sure a lot of people have run into this problem before, the shadows look unalterably crappy. And you can see here when you look through it, it's looking really and behaving really oddly. This is probably where I see the first mistake that people jump into, where they start trying to compile their own shadow pass and they get way, way, way too complicated with it. Again, it's really important. You may not be able to find this always in the documentation, but if you can look deeply enough, you'll discover that Unity literally has one line of code. It's called add shadow. Boom. So don't go crazy. Sometimes it's there and you just don't know it. So all add shadow does is it takes that change that I made to our surface shader and it's added it into its own internal pre-pass depth shader. So what happens when Unity is creating its shadows is it's basically re-rendering your mesh as a separate pass, and in that mesh it has a different shader that it runs in order to do this. And in this case, it just makes sure that this shader carries the informational changes that you've made in the vertex pass, so that when it does its pass, the geometry that it's rendering and the geometry that you're rendering match. So don't go writing another lighting pass if you think the shadows go wrong. First step one is to try and go add shadow. So now let's get a little bit more interesting. So now what we want to do is, again, we want to be able to add in a vertex pass. I'm sure many of you have done this before, but we're going to do this very quickly because this will lead us into what we're doing. So what you want to be able to do is you just need to define, again, you can, much like a normal vert frag shader, you can define a custom vert pass. Now inside Unity, this works essentially the same way as the surface pass does. This is a struct that exists and that will get passed into Unity's vertex pass so that it can do its own calculations and what have you. So let me just delete this out for a moment. So at the moment that's not going to do anything because the struct is essentially empty. I'm not passing through any information that it needs. But the reason why I'm doing this is because ultimately I want to be able to do some cool functions to it. So in this particular case, we're going to, let's go right, so here we go. So this is talking about pragma, what I was just talking about. That lets you define some more complex behaviors that have been predefined by Unity, can be really useful. And we're going to look at global properties in a second, which relates to what I'm about to do. So in this case, I'm going to use, does everybody familiar with what a matrix is, and for the most part what it does? What we're going to be doing is saying, first of all, I need to know, that was not the right shortcut. That makes me wonder what I just did. All right, cool. So, in this case, what I want to do is I just want to get the world position of something. Really simple. The input to the struct is this vertex pass, and then the output here is just a thingy here that I want for my world position, and that will let me get some useful datum out of it. So what I want to do is I want to say, well, I want this object to wave in the wind. Really simple effect. First of all, I want to create a... By the way, this is going to be a really weird looking wind calculation. That's because I wrote it in about 2 seconds and I decided that I didn't really care if it didn't look like wind. So we're just going to avoid being that. All right, so in this particular case, I just wanted to create my own time variable. Again, this is all super simple. Don't worry, we're not jumping too far ahead just yet. And I'm just taking in, again, this is a unity's own, so you can see up here how we have these particular values in here, like half glossiness, fixed color, that are coming from properties. Unity has its own internal properties that are coming into the shader. So when you use something like when you use unity underscore object to world, that is a matrix that Unity is creating on the fly and it's passing through into the shader like a property. Very soon and fairly simply, I'll show you how you can do that yourself. Same goes with time. Underscore time is a global property being passed into every shader. It just has a time value coming from the CPU. And in this case, I'm just putting in a little bit of noise based on where it is in the world. And then what I'm doing is I'm saying, I'm going to create a wind value called my wind. And then we're going to have it wave. So a little bit of code that I've thrown in here, again, to make it look a little bit nice. So you can see, if anybody knows, if you do sine on one axis and cos on the other, that makes something go around in a circle. And then here we're using my wind to just increase the speed. And I'm using text coordinate 1. This is because it just helps me. I've got a secondary texture coordinate on the tree that is essentially a side-on projection. And so a value of 0 means it's at the bottom of the tree, and a value of 1 means we're at the tip of the tree. That just lets me control where and how it bends. Really simple stuff. So if we go into here, we need to... Now, the first thing if I do run it is it's going to say I don't know what wind is. So we need to quickly throw in a... Now, if I were to just run this like this, there'd be no problems, but nothing would run because my wind is currently unset. And this can be another occasion where you can run into problems with nans and you can run into problems with weird undefined behavior. And that is because you've set wind, but you've never put any value into it. So it can be unpredictable as to what's going to be there. Sometimes it can just pull from random memory, which obviously can be a problem because then you have no idea what you're going to get. And you will get some really weird behaviors. Right, and wind, very simply, is a float. So in shader nomenclature, you've got float, halves, and fixed. That just means whether or not you're 8, 16, or 32 bits. And 8 will only go between 0 and 1. So there we go. Now we have a jiving tree. Right, and so now I can duplicate it, we can put a couple of trees around. They're going to look a bit silly, but they're going to look a little bit different depending on where they are in the world, and you can see they bend much more at the top than they do at the bottom. And if you look down them from the top, they sort of look like Doctor Strange. So that's sort of like a neat little trick that can come straight out of the bat. Now, if I turn this into... Obviously, the first problem that we can very quickly come up with is tree texture 2. So these two textures are essentially different materials, but we want them to be able to share the property associated with wind. And it gets out of hand really quickly when you have to go through everywhere and constantly set up separate wind code on every single shader. So we want to turn wind into a global property. Again, really, really easy to do. So we're going to create a script. I'm going to call it global controller. I probably spelled that wrong. I don't care. Just wait until you see the internals of my code. All right. I've heard my style described as variable. All right, where are we? All right, so what we're going to do is, first of all, I'm sure you all know this, I'm going to execute in edit mode. I'm going to do that because I want to be able to see what I'm doing, updating in edit mode. Obviously, really simple line of code. And what we want is, I'm going to be punching two things in, but you're going to see why in a moment. All right. So, sorry, this is my first time using Visual Studio Code rather than Visual Studio. So you're just going to have to. Does anybody use Visual Studio Code to make these little fellas go away? Yeah, all right. You know what? I'm just going to leave it there for the moment. Hopefully it doesn't become too distracting. So, relatively simple. In this one, obviously, it's going to be a public float that lets us adjust how powerful our wind is. And then we're going to do wind setting ID. This is just for a little optimization that we're going to look at quickly. That is, when you're setting a global variable on update, you don't want to do it by a string name because that includes a much longer search in order to do it. So what you want to do is on start or on awake, you first of all want to define the value that variable is assigned to and then call it by an integer value instead of a string name. So in this case, we're saying set property to ID. That is, our property is going to be global wind, and we're going to set it to an ID value. So that in the actual update loop, whoop, there we go. You can see here when we set our global float, we set it by our wind setting ID and our global wind value. And now what we do is we grab our global wind and we simply stick it in our tree wind. We don't need to declare it like we did with the, by putting it in the property block for the actual shader. We just stick the variable inside the shader and it will be readable. So in this case, we just go float global wind. All right. And so now, just to be lazy, my wind equals global wind. I'm dreading to see the little red compile error pop up. It will happen. All right, so I hate having my inspector over there. All right, stick the global controller on there, and there we go. So now we're starting to get a little bit of wind on all of them. And the other thing is now, because this is going to be set also to our tree wind shader, they're all pulling from the exact same global wind value. So now you can set those values globally across your whole project. Nice and super easy. So that's probably just like the first concept to show off and how really, really ridiculously easy it is to do. And then we're going to start jumping into what you can do with that that's even more cool. So, where are we? So we're saying, yep, so that's a global property set up across the whole project. So now we're going to move into, whoa, matrices. So every description I've ever seen written about a matrice is essentially useless. Mathematically, they're very easy to explain mathematically, except for the fact that every use of them is slightly kind of makes you different. Anyway, so like I was talking about, those global properties that we looked at there, Unity has a bunch of these global properties that are also built in that are constantly being passed to the shader. That means that all of these are accessible by your shader at any time, and that means that when you need to perform these functions, you can run it through these matrices in order to get what you need. That is, from object to world, world to object. Most people understand how a matrix works. What it does is it puts it into a new space that allows you to calculate where it is with respect to where your center point is. So for instance, if you're doing a camera, it puts your object in the world with comparison to where your camera is, so that instead of it being, oh, this is at position 1, 1, it says this is at position 3, 4, or whatever compared to your camera going into the screen like this. The reason why this is important, or at least interesting, is because now what we're going to do is we're going to send in our own matrix that allows us to control our fragments from another camera's perspective. So essentially, this is the basis of how all shadow systems work. They capture a depth map from a specific camera, and from there you read that depth map to establish whether or not you're closer or further away from the camera. But you can use it to do a lot of other really useful stuff. So we're going to jump straight into that now. Let me just open it up. All right, let's get started. So we're going to create a new shader. Just make a new standard surface shader, and I'm going to call this basic grab. So first thing we want to do here is start putting in fact, actually, you know what's probably easier? Let's start off with the global controller. So now what we want to do is expand our global controller. Oh wait, actually, let's not do it in the global controller. Let's make another script to do that. So what we're going to do here is we're going to create a script that generates a matrix that we can output into our shader. It's going to be essentially a fairly simple piece of code, and in fact, I'm just going to drag it straight into the project here, rather than coding it live, because I get the feeling we're going to start running out of time very, very soon. So ignoring that for a second, we're going to go straight into this. All right, so first of all, we're going to look at really basic properties that we've put in it. Horizontal resolution, vertical resolution, the ability to put in a custom shader. This will become apparent when we're starting to do stuff like creating our own render textures in it. So we'll ignore that for a second. But what we're going to look at is our public references, private references here, right? So what we want to be able to do is send out, here's where things become interesting. So what we want to be able to do is say, well, I want to create a matrix that's specific to this camera. So first of all, what we're going to do is we're going to say, well, let's grab our camera. We need to make sure that the camera is not on, because what we want is just the matrix associated with it. The camera's not going to actually do any rendering. And if it does rendering, we're going to get it to do it while it's under our control, because we can then tell it to do very specific things. So the first line that we've got here is we're saying, well, I need a render texture, so let's create a new render texture when it wakes up. Set it with the horizontal and vertical resolution. And in this case, I'm sending the render texture format to being depth, but we'll come back to that. So that's just what that sort of basic stuff here is. And again, I'm doing the really simple property of setting a property to an ID, property to ID, because these are going to be the things that I need to send through, right? So I want to send through, just for the moment, we're going to focus on sending through the matrix from the camera. That is, in this context, we're calling it the cam matrix. And the way we make the cam matrix is we want to be able to build it from our camera. So our camera is a variable here. We're getting the component from this game object, because this will be a script that we're going to attach to our camera. And what we want to do is we want to get a variable. In this case, I've done var, but I tend to be opposed to using, I like to type my variables. I haven't done it here. These are all 4x4 matrices. So all your cameras have a set of properties associated with them that can be run in order to get the matrices out of them. So in this case, what you want to do is you want to get the world to camera matrix. This will take any point within the world and it will translate it with respect to the camera as if the camera was just a single point in the world. That is it in front, behind? Then you want to get the perspective matrix. This is really important because that's how the cone of your camera is skewed based on perspective. Or if you're using an orthographic camera, it's how it's sort of not skewed according to that. So then you multiply them. Again, really nice thing about matrix, if I multiply both those matrices together, that one matrix functions as though I've done one after the other. So what we want to do here is we want to get the perspective matrix, multiply it by our dimensional matrix, and in this connection we want to do GL get GPU projection matrix, and what that does is it creates the matrix we need in order to be able to understand where something is within a render texture. So it'll give us our coordinate system not within world space but within screen space, essentially. This will become really important in a moment. And so in this case, what we do is we put our cam matrix into it, and we say, yes, this is going to be something that's going to be able to render into a texture, and we turn it into our projection matrix. So now we've constructed a matrix that can be used by this camera and can be read by our shader in game. So you can see here, I've set global matrix, cam matrix. So first of all, let's put a new camera in. Oh, sorry, I'm in 2017, which I don't use typically these days because I am still trapped in 5.6. Yeah, so there we go. And then what we want to do is, sorry, it's called Tin Matrix Cam. That's just because it's, I may have used some of this code in Tin Man. All right, so none of this is enormously important right now. And you can see here that our camera is off because it really doesn't need to be on in this circumstance. All right, so now, sometimes in this particular case, because I've set up the code a little bit poorly, I'm just going to quickly press play because that does it on start, not await. All right, so now what we want to do is we want to create our basic grab shader. So what we want to be able to do is in our shader, we need to be able to use that matrix in a way that could be described as useful. So the first thing we want to do is put in the information so in order to use the matrix. So now that's a global property, we can access it like any other property in our setup. There we go. It's a float 4x4. So the easiest way to think about a matrix is, I find, thinking of it as 4 float 4s or 3 float 3s. It's essentially a set of floats. Each one, a set of vectors. Each one is distinguishing a part of the new space that you're translating into. So for instance, in this particular one, the third row is actually just the forward vector of your new matrix. That is, where is the forward vector of our camera? And that can be really useful when you're trying to do things a little bit later down the line. So we've put the camera matrix in there, and the next thing that we want to do is we want to say, well, I want to turn this into a set of UV coordinates. So the first thing that we need to do is we need to put in a vert pass like we did before. So I'm going to do that right now. This way we can pass out custom data, basically, from our vert path. So there we go. Then what we want to do is, because of the nature of our struct, we need to add a little bit more information into the struct. Now the thing you need to understand is in the background, Unity is also adding information into that struct as well in order to up to a maximum amount, depending on the pragma target that you're targeting. If you want to fit more in there, you may have to go up a target. Because in a surface shader, Unity is already including a lot of stuff like world position and all these other useful little tidbits that they use later down the line. So it is actually there, you just don't know it. And sometimes in order to just access it yourself, all you have to do is just type it into this socket here and you'll be able to read it without doing anything in the vert pass. But in this case, we do want a vert pass. So here we go. Now, this is going to look a little bit confusing because I'm about to extrapolate something in a slightly useful way, slightly. So in this particular case, what we're doing here is we're saying, well, first of all, we need to get it to the world, because what our matrix does is it is translating from the world into our camera perspective. We can't go from the object's perspective straight to the camera's perspective. So we get our vert in world space, and then what we do is we multiply our camera position by our camera matrix. Now we have that emission in camera space. Woo! Straight out of the gate. Well done, Edward. Ah, there we go. So actually what I've done is grabbed the wrong thing, because this is exactly what I knew was going to happen in front of everyone. So what I've done, because this is interesting, I have not... Alright, so in order to try and simplify things up a little bit, I'm going to teach a nice little trick which is really useful. So I'm sure people here, if they've actually had a chance to really play around with it, you can create your own... really hard to see here. You can create your own functions inside your shader programming to try and simplify things up and turn them into single lines to make life much easier. So in this case here, I've defined a function. It can be void in this case because we're returning our own out here, right? So what that means is I need to specify what my out is. In this case, it's o.campos because I've declared it up inside my input. And I'm saying inside this little bit of code, all I want to do is be able to input a vertex position. That's what our pos is, because we're going to use it here and we're going to use it here. And I want to return a result. So this way, when I put into my vert pass, all I need is that one line. And it will take in my vertex and it will output campos. really nice, neat little bit of code to write, and this will become really important in a moment because soon we're going to set it up so that anybody can access that piece of code from anywhere. And that's when we're going to be getting onto CG includes. When what you want to do is set yourself up something very complicated and you want everybody to be able to do it. So there we go, we have that little bit of code there. So now what we want to do is we want to say, well, what's the point of having our what's the point of having a matrix? How can we use this usefully? So in this case, you saw previously that I was setting up in my matrix camera. We've got a value here saying public texture cookie. So in this case, this is an image that I want to be applied through my camera. It's a public texture variable. And what we can do is, like we did with the matrix, we can assign a texture as a global shader property. So in this case here, you see set global texture, and we're setting it as cookie, and the value is the static texture of the cam, which is an ID number that we did back up here in the same way as we did it before. That is, the property ID is called cam static texture. So if we go into our basic cam, what we want to do is go, here's our camera static texture. We'll drop it in now, so it can be read. Whoopsie daisies. I'm sorry, I'm not very used to using Mac, so I keep not actual copy and pasting. All right, there we go. So, cam static texture. Brilliant. So there's our cam static texture. It's now a value that can be read through. So now what we want to do is we want to be able to read that texture. So we're going to grab it here. There's two lines that will be nice and easy. So that's our main texture that's coming from there. We're actually just going to do a straight replacement, but I'm not going to edit out those lines because we're not worried too much about performance at the moment. So first of all, we need to turn that matrix into a set of UV positions. So that's what we're doing here, cam UV. And again, what I'm going to do is I'm going to separate out my camera UVs into a separate function to make the construction of that UV position a little bit easier. There we go. And now remember, an inline just means that when it compiles, it will actually just drop that piece of code inline into the compiler. That will help with certain things running a little bit faster and making sure some things are executed in the right order. So in this case, we want to add a set of camera UVs. So what we do is we put in the raw UV that we want to turn into the camera UV, and we have to do a little bit of operation to it. In this case, we're inverting our Y, and that's just because dependent on system, your Y position can be from 0 to 1 or from 1 to 0. If you look inside the documentation, Unity points out which devices read it in reverse. They also have an if-def statement that you can use that says, if Y up, do this. Very simple little piece of code. And here we've multiplied it by 0.5 and times it, added 0.5, and that is simply because we want to be able to read our coordinates in the camera are currently at the center of the camera, and we want it like a UV coordinate to be reading from the bottom left, essentially. So we are halving its length and then we're shifting it right so that it never goes into the negative, because what coordinates it gives us is 1 to -1 starting in the middle. What we want it to give us is we want it to give us 0 to 1 starting on the left. So that returns us a standard set of UV coordinates we can use, and now we can read the static texture. So provided nothing has gone too badly wrong there. So now what we need to do is we need our camera to actually have a useful static texture in there to read. So let's quickly drag in something that we can use. The letter A. We grab our camera, drop the letter, oops, that's not where it goes, there we go. Drop the letter A into our cookie, and we're going to set our floor texture to a new material. Well, that's not what I wanted. For a new material called cookie. No, let's try that again. There we go, cookie. And we're going to make this our custom basic grab, and there you can see an A is now being projected onto it. And that A is being projected onto it from the angle of that camera that you can see there. So that camera is now dynamically creating a set of UV coordinates that I can use in any space from any shader in order to look that up. So now what we can do is you can look at the letter A, and you can see in this case, if I were to change my field of view, you can now see lots and lots of little A's, and that's because my texture tiles, so that when we go above 0 or 1, it just wraps around. You can solve that problem by simply going into our texture and making sure that it does not repeat. If we clamp it, then you just get a little A. And now you can see that the field of view, that was our projection axes, and you can also see that our positional axes will be based on where our camera moves, and we can now do that kind of performance. Everybody with me so far? I'm not going too fast? Anybody's minds bleeding yet? Awesome. All right. So now we're going to start getting fun. So now we're going to go and we're going to update that, because it's like, that's really cool, but now we can do really much more interesting stuff with it. So straight off the bat, if we go back into our play mode here, you can see here from that code that we were looking at originally, I'm telling my camera to generate a texture. And in this case, it's a little bit hard to see, so I'll move the camera a little bit closer. We are generating a depth map from it. There we go. So why this is significant is it means that this particular depth map that's being generated from the camera here will allow us to do some interesting effects, because now we have, this camera is providing us information about the world. So if we go back into the camera and we go into our matrix, you can see here that we have our same matrix, because of course that texture is coming, that render texture is coming from our innermost plane, essentially. So that will really help us do it. So now what I'm going to do is I'm just going to actually bring in a shader that's already written. Now functionally, this is very, very similar to our other one, but now it allows us to get a little bit of render depth from it. So, whoopsie daisies, let's just stop that. Whoopsie daisies. What's render depth called? You don't look right. Huh. You're very broken. My apologies. Oh, of course. Wrong shader. Sorry. Naming systems. I suppose it makes sense because that one was called basic grab and this one's called basic depth. All right. So one of the areas in there is that you can, when you want your camera to render but it's not on, you can simply run a function. It's called camera.render. Very simple. It means your camera's not on, it's not rendering, it'll only render when you ask it to. If you want to do static depth maps, you can do it straight out there. So in this case, you can render with a custom shader. So because it's a little bit expensive to be rendering everything, I can stick a custom shader in this case, which is render depth. This is simply a very, very simple Unity shader that does nothing but render out depth. Although, at the moment, it's probably not necessary because Unity's sort of already doing it itself, but we'll just throw it in there anyway. So, now what we want to do is we want to go in and we want to say, well, here's our custom basic depth. So that's going to get rid of that because it's not using any of that, but put a little cube into our scene. And let's put our cookie texture on you as well. Cool. All right, there we go. So now we go to our camera. Make sure that we're setting up to custom render here. And let's get our, and now let's see how straight out of the bat I'm not working. Oh, did I? Ah, yeah, I put basic depth. Oh, no.
The other one had render depth. On the camera?
No, the camera's been put into there. I think I've probably just not turned on what I'm supposed to be doing. All right, so in this particular one, what we're trying to do, obviously, is read the... Whoops, that's basic grab, sorry. I do want basic depth. So inside basic depth, essentially what we're doing is we're doing the same unhook camera UV. We're getting our camera matrix out UV, which is what we did before. The only difference here is that I'm now also, instead of just applying it as a multiply, as I was doing before, just applying it as a texture, in this one I'm analyzing the raw depth from the camera texture, and then I'm also doing another little calculation, which is distance Z minus distance W. So in those UV coordinates that we sent out from the camera, when we sent it through the matrix, because it's now in that camera's space, Z is how far away are we from the camera. And we divide it by W because W is the value that's adjusting everything by our perspective. All right, so hopefully we'll be able to get there. Unfortunately, I am running well behind, so we're going to have to... let's run this a little bit faster. Here's one I prepared earlier. So, boom. No. Why would it? Thank you. All right, cool. So here we go. So in this particular context, what we're doing is we're doing exactly the same thing, but you can see here that if I turn off our Intrepid A, which seems to be getting in my way. Let's turn you off. Oh. Oh, I guess because it defaults to black. There we go. Let's just put that on it. That'll do for now. All right, so you can see here that this black outline here is being created by my camera's viewpoint, that shadow calculation that I was showing you before. So I'm reading the shadow map and I'm just determining whether or not that pixel is at a further distance than that camera. So now what our camera does is it is creating a fake secondary shadow there. I think you can just see it down there. Again, all it does is we're reading the, whoopsie daisy, sorry, if I drag it off completely. So you can see here where one of the dysfunctions comes from it, which is that you have to adjust it for being outside the fulcrum. That's just a calculation that you have to do. In this case, because I haven't done it, it will default to black. But usually what you have to do is you just have to stipulate what happens if I'm outside that fulcrum. So you can see here the little shadow volume. Unfortunately, I don't have a huge amount of time left, so I'm going to have to blast through the sort of final concept. So in that particular one, you can see that our shader is, becomes quite interesting and a little bit complicated. That is to say, that's where we're doing our shadow function. We're simply saying how far away from you the camera and what are you reading out of the depth map. If you're different, and in this case I've added a 0.7 just to make sure it's not completely dark so you can separate it from the main camera's shadow. And I've said just multiply that shadow value in. And in this case I've turned the shadow into a single function. But this gets complicated really fast, so what you want to do is you want to try and do something called a CG include. And that's what we've done here. So let's go to a core include. It looks exactly like a shader file, but it ends with .inc, standing obviously for include. So in this particular context, you start off by saying this is just an if-def for you. You don't have to use it. Core include included. This is just if I ever need to make sure whether or not this value is included. I'm using a C buffer here. This is a constant buffer. It's good practice if something is being accessed a lot but not being updated a lot. That is, it only gets sent through to the GPU once, basically at the beginning of the cycle. C buffer N. So these are my standard my standard properties that every shader I want to use it is. And then here are the functions that I'm using. Those you saw that I wrote previously. We just drop them straight in our include file. And now when I go to our basic, so what I did is a nice little technique here for our particle system. So I want to be able to use this same stuff to be able to create some other really neat effects. So if I go into this shader here, you can see I've said, here we go, include. Now there is a way to do this without specifying the total position, but each one suffers a problem. If you specify the position explicitly and you move it, it will get disconnected and it won't be able to find the assets that it needs. If you set it relatively, if you move this file, it will lose it and not be able to find its assets. So no matter what you do, it's going to, one or the other file moving will cause it to break. So in this case, you just say include and put the exact specifier for your include file. And so now I don't have to include any of the stuff that I was just doing, except our cam pos. So we've got that camera matrix out. You'll note that that's not been clearly defined. It's in our include file as we did it in our previous shader. And I've just dumped it in. Cam pos I have to add into here because in order for the data to travel through and for Unity to be able to assemble it, then what it needs to do is it needs to be in our struct and we need to be outputting it into our struct. So you have to make sure you put it in. That's why for all of your functions that you write, they're not going to be able to read vertex unless it comes through with the struct. So for the raw information, that is the data you're using that comes from the shader, has to come as an input, and anything that you're using that is a property only needs to be defined within the include file. So in this case, what I'm doing is I'm outputting our camera matrix at position, and then what I'm doing is I'm using our single line saying shadow, and all our shadow calculation needs is our camera position coming in from that vertex. That we get our shadow value, and in this case, what I'm using the shadow for is I'm saying I want you to become darker if you're not in shadow, because what I'm creating is a really simple little system so that here's a particle system that only shows up in our artificial shadows. So if I press play, I've set this up to rotate. So you can see here, using our CG include file, I can drop it straight onto any shader that I want using an include, 2 lines of code, and 1 input struct addition, and I can now add those lines of code that I spent that time putting together to be able to create an effect that can read from this. Now in this case, I'm reading from my own custom camera depth, but you can read from unities directly. You just have to be careful because obviously Unity tends to do things so that they're efficient. This isn't necessarily the most efficient way of doing things. What Unity does it in this case is try and compile them all into a single texture that everybody reads from. So it can be quite hard for you to be able to determine a specific shadow volume because in order to prioritize that, you might have to create your own shadow volume. So if we jump back into here, we're getting very close to the end there. Yep, custom camera matrix. Decoding Unity, so if you get a depth map from Unity, here's camera depth texture, that's what Unity sends through as its global depth texture property. And when you want to be able to render, that's your custom render type. And decode iDepth is what you use to decode Unity's render textures for their own depth maps. In that case, the reason why I was able to decode my depth map just as a simple comparison is because my depth map was literally just depth as a 32-bit. It's like a float, like a depth as a float texture. All it does is it stores one big number that can be a float, and it can go from 0 to as big as a float is, obviously. And then we have our custom includes. This also goes to what I was talking about before, where sometimes Unity does things a little bit smarter. Some of their own internal stuff are put in constant buffers. So sometimes when you try to replicate their behavior, you won't be using constant buffers, and you can sometimes undermine some of the optimizations that they've done. Also with CG includes, don't go crazy. I have had to edit shader files that are made up of about 16 to 17 nested CG includes in the most just impossible way to translate. You want to try and divide them up by simple behaviors that can function as much as possible on their own. Because otherwise, this CG include needs this one, which needs that one, which needs that one, which needs that one. And I've seen some pretty daft ways of setting it up, including and not limited to one CG include that is just all of the properties and another one which is the functions, and it just becomes a nightmare. Cool, so that's managed to cover, I think, most of that sort of how to globalize a lot of different shader effects and what have you. Unfortunately, I'm not going to have time to go into any major detail regarding some of the lighting stuff, but it works. Once you sort of start to play around some of this stuff, you'll see that it works Unity's internal lighting works similarly that is Unity CG includes are bringing in functions that allow you to do that. So if I were to dig up very quickly into one tiny last thing. So for instance, in a current unannounced Tin Man project, we're doing multiple forward lights inside forward pass so we don't break dynamic instancing. So you can see here, I'm inputting a whole bunch of different tin lighting elements in a big buffer. And then in order to create my shaders get complicated fast. All right, so in order to create it, I have literally, so wherein Unity has the thing what they call, we're creating a Unity light, it looks like a Unity light, and it is a type that is a struct that's a Unity light. That's how Unity does its little individual lighting. So what I've done is I've just grabbed Unity's code. I've created my own surface output. So I've called this surface output standard multi. Once you realize that all a Unity's lighting function is a struct that you fill, that you use somewhere else, I created my own struct. And then in Unity standard lighting, I've said instead of the input struct being Unity standard, I've said make it Unity standard multi. And I've just edited Unity's basic lighting code so that instead of doing one light, which is just that line, I've said do it 5 times additively and use each one of my lights each time. 1, 2, 3, 4, 5, whatever. So in this way, now we have forward-based lighting that does 5 lights in a single pass. It doesn't break dynamic instancing, and it also lets us do it a lot cheaper in forward without having to do multiple lights. And again, it just continues to build on these basic principles. This can be done in any shader, and all our globals are stored in our, I have no idea why that just happened. Right, that's a really interesting way of presenting information. Anyway, that's about time to call it, I think. Do we have any questions? No, we don't have questions. I'm getting a no from the back. If you have questions, just come and ask me. Sorry, I ran a bit over time. But, yeah, there we go.